Hi everybody. I wanted to go through some more of the Lewis structures that we started on Friday. So I'm going to kind of skip around so that way we can see a variety of them because there are a few that I want you to try on your own. So we did A and B together in class. I want to go next to C. We'll just go down in this row, but then after that we'll kind of skip. So let's look at C. On C, it says PBr3. So if we wanted to name PBr3, it would be phosphorus tribromide. Remember that we said that the first thing that we're going to do when we draw these Lewis structures is that now we're going to count the total number of valence electrons for the entire compound. So I know that phosphorus has how many valence electrons? How many valence electrons does phosphorus have? And you know that it has 5. Now I want to know how many valence electrons does bromine have? Well, bromine has 7, but there are 3 of those bromine atoms, so it's really going to be 7 times that 3. So I'd have 5 plus 21, that gives me 26 valence electrons. So PBr3 has 26 valence electrons. Okay, so again, PBr3, our goal is to have 26 valence electrons. The next step is to just try to make some type of skeletal kind of structural model for this, and we need to pick out a central atom as well. So I know that phosphorus is least or less electronegative than bromine. So phosphorus is going to go in the middle. It will be our central atom. And then that means that bromine, Br, are going to be the surrounding atoms. And yesterday we said that surrounding atoms also have another name. Those are ligands. So phosphorus and bromine will be our surrounding atoms. Okay, so here's our structural formula. So this just shows me like bare backbone. So I see phosphorus, I have my 3 bromines, so that fulfills my molecular formula. So let's count first how many electrons that we have present here. So we have 1, 2, 3, 4, 5, 6. I need 26 total. So right now I have 6, so that means I need 20 more. So the first thing I want to do is make sure that my surrounding atoms have that octet, or they're full with electrons. So I know that bromine has 2 right now, so it needs 6 more. So I'm going to do that for each of these. So I have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay? So now if I count all of these up, we had 6, plus another 6 is 12, plus another 6 is 18, plus 19, 20, 21, 22, 23, 24. So now we only have 2 valence, or we're only 2 electrons away. So all of my bromine atoms, their octet is fulfilled, so I don't want to do anything to them. So now that means I'm going to look at my phosphorus atom, my central atom, next. Now I see that phosphorus has 1, 2, 3, 4, 5, 6. So it wants an octet, right? So if it has 6, then I'm just going to place this lone pair of 2 up there. So here would be 25, 26. Now we have to check to see if this is right. And we're going to check that by doing a formal charge calculation. So if the formal charge of phosphorus is good, if it's 0, then that means that how we've drawn this is correct. So remember that formal charge is F, which is formal charge, equals the number of valence electrons minus N is, do you remember? N is the number of electrons that are in lone pairs. So that would be like, here's a lone pair, here's a lone pair, here's a lone pair. So that means that I would have 6 electrons that are in lone pairs, just to help remind you what a lone pair is. So valence electrons minus electrons that are in lone pairs plus B over 2. So B, remember, was that number of electrons that are in bonds. So if I'm just looking here as an example for bromine, I see that I have 2 electrons that are in a bond here for bromine. So I would say that B for this one was 2. Okay, so let's calculate formal charge for phosphorus. So I'm trying to calculate formal charge. I'm just going to write a little p down here so that way you know I mean the formal charge of phosphorus. So the formal charge of phosphorus, first I want to know how many valence electrons does phosphorus have? Well, we use that whenever we calculated this up here for 26. So I can look on my periodic table and I can see that the valence number of electrons for phosphorus is 5. So I'm going to do 5 minus. N is the number of electrons that are acting as a lone pair. So I only have one lone pair on phosphorus, and that's this right here. So it's this right here. That's my lone pair. Right here. That's my lone pair for phosphorus. So that means I have 2 electrons that are acting as a lone pair. So I'm going to do 2 plus. Now, the next one, letter B, that represents how many electrons are acting in a bond. So if I look here, I have 1, 2, 3 bonds, and each of those bonds has 2 electrons each. So here's 1, 2, 3, 4, 5, 6 electrons. So I'm going to do 6 over 2. So if I simplify this down, it'd be 5 minus 5, which gives me a formal charge for phosphorus of 0. Yay! So that means that this is the correct Lewis dot structure for phosphorus tribromide. Now, I think that this is a pretty easy one, and you can tell that this wouldn't be some type of exception here. So phosphorus could very easily make this, and I think this is one that you could have drawn already before. So let's try another one. I want to skip, guys. So we've done A, B, and C. I'd like to skip to... I'd actually like to skip to letter H. Letter H is CH3OH. So let's look at letter H. That's CH3OH. Now, again, the first thing we need to do is calculate the number of valence electrons that this entire compound has. So carbon, we know, has 4, plus I have 3 hydrogen here. So hydrogen each has 1 valence electron, but there are 3 of them. So that means that this would be 3, plus oxygen, which oxygen, we know, has 6 valence electrons, so that'll be plus 6. And then I have this one little extra hydrogen atom here, so that would be plus 1. So if I had 4 plus 3 plus 6 plus 1, that gives me 14 valence electrons. Okay, so we have 14 valence electrons here. Now, we have our number total of electrons. Now I need to try to pick out a central atom. Now I know that hydrogen can never, ever, 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 ever be a central atom because it's always a surrounding atom. And oxygen, so that leaves me with carbon and oxygen. So I know that carbon is not as electronegative as oxygen is. So that means that carbon's going to be my central atom. So I have carbon here. That carbon is surrounded by 3 hydrogen. So we'll just say, here's a hydrogen, here's a hydrogen, here's a hydrogen. So I have this carbon surrounded by 3 hydrogen atoms. So we have those there. Well, next I have an O. So here's my oxygen. And then that oxygen is attached to another hydrogen. So this would be my structural formula for CH3OH. Okay, so my goal is ultimately to get 14 valence electrons. So let's look to see how many that we have first. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that means right now I need 4 more electrons to be shown somewhere on this structure for my Lewis structure. So first we want to look at the surrounding atoms. So we have hydrogen surrounding pretty much everywhere. So this hydrogen's good because it has 2, this has 2, this has 2, this has 2. So all the hydrogens are good, I can't touch those. Let's look at carbon next. So carbon wants to have 8 electrons around it, and in this case, does carbon have 8 electrons around it? You should be saying yes, because this is 1, 2, 3, 4, 5, 6, 7, 8. So should I do anything now to the carbon? No, because it already has 8. So the only thing that really isn't fulfilling this octet rule is what? Oxygen. And I have 4 more electrons that I need to show for me to get this 14 valence electrons fulfilled. So oxygen has 1, 2, 3, 4. So how about if I add 4 more electrons around it? 5, 6, 7, 8. So now that means that oxygen would have 1, 2, 3, 4, 5, 6, 7, 8. So every single element here has a full octet. But, again, what should we do? We need to calculate the formal charge. And I actually, in this case, want to show you the formal charge for both carbon and oxygen, just to show you that they would both be equal to 0, okay? Now, carbon, let's do the formal charge for carbon first. So, formal charge for carbon would be the number of valence electrons for carbon, which is 4. So 4 minus. Next, I want the number of electrons that are acting as lone pairs. So do I see any little extra dots as lone pairs around carbon? And we should be saying no. So that's 0. Next, I want to find the number of electrons that are acting in a bond. So 1, 2, 3, 4, 5, 6, 7, 8. So I have 8 electrons that are acting in a bond. That's going to be over 2. So if I look at the formal charge here, it would be 4 minus 4, which gives me 0. So our formal charge of carbon is really good. It's okay. So I know carbon's good, but now I want to just show you that oxygen is going to be 0 as well. So let's do the exact same thing here for formal charge, but we're going to do it for oxygen now instead. Okay, so instead of carbon, this is going to be oxygen now. So if I look for the number of valence electrons for oxygen, we know that that's 6. So I'm going to have 6 valence electrons minus, that 6 is really messed up, guys, I'm sorry, let me fix that. Okay, so I'm going to have 6 valence electrons for oxygen. Now I'm going to take that minus the number of electrons that are acting as lone pairs. Well, this is a lone pair, and this is a lone pair. So that means that total, I have 1, 2, 3, 4 electrons that are acting in a lone pair. So I'm going to do minus 4 plus the number of electrons that are acting in a bond. So here's 1, 2, 3, 4. So then I have 4 electrons that are acting in bonds. So it'd be 4 over 2. Okay, so if I look here, if I simplify this, this would be formal charge of oxygen is equal to 6 minus 6. So formal charge of oxygen is 0. Yay! So that means that this structure that we drew here is perfect. Okay, let's do another one. Sorry guys, phone's going off. Okay, let's do another one. Let's pick, so we've done A, B, C, we've done H. Let's look at, I want to do 2 more with you. Let's actually look at letter I. Let's look at the last one. That last one is C2H4. So this last one is C2H4. Okay, if I wanted to calculate first the number of electrons that are present completely in this compound, C2H4, I'm going to add up 4 valence electrons for carbon, but times 2 because there's 2 of them, so that means that there are 8. Plus, hydrogen has 1 valence electron, and there are 4 of them, so that would be plus 4. So that means that overall, I have 12 valence electrons. Okay, so I have 12 valence electrons. The next thing I need to do is pick a central atom. Well, I have carbon and I have hydrogen. Hydrogen can never be a central atom, so that means that I have to use carbon. So I'm going to have carbon, and it's going to be, there's 2 carbons.